Hello everyone and welcome back to the linear algebra component of the Calculus and Linear Algebra series. In the last video we introduced the idea of a proposition, and more importantly we introduced the idea of a propositional variable. That was a variable that takes values in the space of propositions. And in this video what we're going to look at is we're going to look at a new concept called a logical operator or logical connective, which we can simply just think of as a function that takes in propositional variables and spits out new propositional variables. So let's go to our definition now of what a logical connective or operator is. So we say a logical connective or operator is an operator that takes in one or two propositional variables and produces a new propositional variable. So an example could be something like a function, right, that you have in school, that it just takes in, you had a function that takes in numbers and spits out a new number. But in this situation now, our logical operator is something that takes in, rather than numbers, it takes in propositions and produces new propositions. And we'll see what type of operators those look like in just a moment. But we also have a name for these two different types of logical connectives. So the ones that take in a single propositional variable, we call the unary operators. And the ones that take in two propositional variables, we call the binary operators. And for this video, we're just going to focus on the unary operators, and in the next video, we'll look at the binary operators or logical connectives. So you might ask, well, what type of propositions consist of ones that contain logical connectives? And that's where we end up with this idea now of a compound proposition. So we think of a compound proposition as a propositional variable that contains logical connectives. So if I've got some propositional variable that has logical connectives inside it, then we think of that thing as a compound proposition, because it consists of multiple things. It not only consists of a propositional variable, but it also consists of a logical connective or operator. And we say the types of propositional variables that don't contain any logical connectives, we call those the atomic propositions. So what can you think of the atomic propositions are? So the atomic propositions are simply just the propositional variables themselves that we started off in the first lecture. It's just simply a propositional variable that contains no other pieces. And then that kind of makes sense why we call these the atomic propositional variables or atomic propositions, because let's think about the derivative of the word atom. Well, atom simply just means that, comes from the Greek to mean indivisible. So an atomic proposition is something that can't be divided up into any more subparts. And now one of the useful concepts to be able to introduce is the idea of something called evaluation. So evaluation is an assignment of all the possible values a compound proposition can take, given all the possible values of its component atomic propositions. So this seems rather waffly and a little complicated, but the idea is that if you're given a compound proposition, that compound proposition can only take the value of true or false. And which value it takes depends upon the individual atomic propositions that make it up. So if I run through all the possible truth values of the component atomic propositions, then I can deduce what the truth value is that complicated compound proposition is. And it might seem like this is a very algorithmic way of doing things, and therefore we might want a table. So now we introduce the idea of something called a truth table, which is a particularly useful way of constructing valuations. So it's simply a table that's constructed by running through all the possible truth values of the component atomic propositions. So again, this is a little bit confusing, but you'll see how this works in just a moment by actually getting hands-on by doing some of these truth tables, and you see it's actually very intuitive. So far we've introduced what a logical connective is. We've introduced the idea of a compound proposition, which is propositions that consist of these logical connectives, and we've also seen how to create valuations of these types of compound propositions or compound proposition variables. So what type of logical connectives do we talk about? Well, we said now there's the single operated logical connectives, which is the logical connectives that take in a single propositional variable or map out a single propositional variable, and those were the unary operators. So let's define the unary operators. Well, the unary operators are written as follows. So we have this kind of L on its side, we have this id operator, we have t, and we have the upside down t. And in fact, these are all the unary operators that can be defined on the propositional variables. And that's fairly easy to see because the propositional variables can only take the value of true and false, so it's only possible for there to be 4 unary operators on a single propositional variable. And let's go through them individually. So if I go to this first one here, which is this kind of L on its side, I call this the negation operator, and we'll see why it's called that in just a moment when we fill out the truth table. We have this id operator, which we call the identity operator. Again, we'll see why that's called that. This T here stands for the tautology operator, and the final operator that we have here, which is this upside down T, is called the contradiction operator. And again, we'll explain why the origin of all of these things in a minute. So what we're going to do is we're going to start our truth table. And our table looks something like this. We start with P, which is our propositional variable, and P, because it's a propositional variable, can only take the values of true and false. So let's just put on in our table true and false underneath the value of P. And we want to define what does this negation of P mean? Well, negation of P is going to be the thing that negates the truth values of P. That is, it takes a truth value and maps it to false, and it takes a false value and maps it to true. So the negation operator simply just flips the truth value of whatever propositional variable you have. And that kind of makes sense, right? That's what negation means. It's just the opposite of what the original truth value was. So what's our next piece? Our next piece is the identity operator. Well, the identity operator is just another way of saying it's an operator that doesn't do anything to the truth values. So that's to say that it takes a value of true and maps it to true, and it takes a value of false and maps it to false. So it's a very simple operator. It effectively does nothing to our truth values. So the next operator is the tautology operator, denoted by this T. Well, as you might expect, what it does is it takes the value of true and maps it to true, and it takes the value of false and also maps it to true. That is, it sets all the truth values of the original propositional variable just to the value of true. And the final one, which is the contradiction operator, now hopefully you might expect what the answer is to this. That's simply going to map everything to false. So it takes a value of true and maps it to false, and takes a value of false and also maps it to false. And that's the contradiction operator. And if we just look at these final 2 operators for a minute, well, we see that whatever they do the same thing to every single propositional variable. So it's regardless of whether or not the propositional variable was P or Q or any propositional variable. So you often see this notation that you can get rid of the P in this table. So you sometimes see the tautology operator rather than that written as just this, because it does the same thing to all variables. And similarly, you see the contradiction operator written in this way, as it also does the same thing to all the variables. So this is our truth table, and this is what has defined our unary operators. We can see that the contradiction operator just does what it does to these truth values here, the identity operator, the tautology operator, and the contradiction operator. So I explained at least what the negation operator and where the word negation came from, and where the identity operator and the word identity came from, but why do we have this tautology and contradiction operator? And that leads us to our kind of final definition here of what we mean by a tautology and a contradiction. So a tautology is a propositional variable whose valuation is always true. So that is, imagine you're given some compound proposition. It's built up of lots of individual atomic propositions, and no matter what values those atomic propositions take, whether or not they're true or false, the overall compound proposition is always true. And we'll see some examples of that in the next video and how to prove that that is the case. But a simple example I can give now is something like, my name is James, or my name is not James, right? That must always be true regardless of the individual truth of those statements. And as you might expect, the contradiction, or a contradiction, is a propositional variable whose valuation is always false. And now this makes sense why we named those things the tautology operator and the contradiction operator, because they simply take all the values to true and all the values to false, which is consistent with these definitions of tautologies and contradictions. So that's where we're going to finish the video now. We've introduced the idea of a logical connective. We've also talked about compound propositions, how to take the valuation of compound propositions using truth tables, which we'll extend on more in the following videos. We've introduced all the unary operators, and also introduced the definition of a tautology and a contradiction, and motivated all those single operators in that unary operator table. And next time, as you might expect, we're going to move from the unary operators to the binary operators, which are actually the ones that are much more ubiquitous in mathematics and are going to be far more useful. And even further, we're going to use our truth tables to prove some tautologies about some compound propositions. So thanks very much for watching. Again, please look at the notes on the Moodle page afterwards, and I hope to see you in the next video. Thank you.